Hi everyone, this is Gushu from University of California, Santa Barbara. Today I'm going to introduce our ASPLOS paper towards efficient superconducting quantum processor architecture design. Superconducting circuit is one of the leading technologies in quantum computing. To augment the computation capability of superconducting quantum processors, people are trying to integrate more qubits and more qubit connections. The reason is that if a quantum processor has more physical qubits, then it could run a program of a larger size with more logical qubits. More qubit connections on a superconducting processor can directly support more 2-qubit gates on more physical qubit pairs, making it easier to route logic qubits among the physical qubits, and thus reduce overhead in qubit mapping. For example, IBM's first generation public superconducting quantum chips on cloud are 5-qubit chips. The second generation is a 16-qubit chip, and the qubits are placed and connected in a 2x8 lattice. The third generation is a 20-qubit chip, and the qubits is on a 4x5 lattice. The connections are denser. Some fiddle qubits can connect to 6 other qubits around it. However, this picture shows the qubit layout and connection of IBM's latest 53-qubit chip. The interesting fact we can see here is that the connection on this chip is very sparse compared to its predecessors. Most physical qubits only connect to 2 nearby qubits. Why? The reason behind the sparse connection is the low yield of superconducting quantum processors. Little attention was paid to this problem before. However, the yield problem is indeed hindering the development of larger scale, more complex superconducting quantum processors. For example, as reported by IBM, the yield rate of a 16-qubit chip under their state-of-the-art technology is only around 1%. Before we discuss about how to optimize the yield, let me first introduce some necessary background to help you understand superconducting quantum processors and where the low yield comes from. The background knowledge we are talking about here is mainly from IBM. So in this work, we consider a type of qubit called fixed frequency transmon qubit. One transmon is an anharmonic oscillator consisting of a capacitor and a Josephson junction. When we put this anharmonic oscillator in a fridge with very low temperature, it will have discrete energy levels. We use the ground state of this oscillator as a 0 state and the first excited state as a 1 state. The energy gap between the ground state and the first excited state is E01. The frequency of a transmon is defined as the E01 divided by the Planck constant, denoted by F01 here. Similarly, we use E12 to represent the energy gap between the first excited state and the second excited state. We can also calculate the frequency F12 between them. Since this oscillator is anharmonic, F01 and F12 must be different. The anharmonicity parameter delta here is defined by F12 minus F01. To give you an idea, a typical qubit frequency for IBM is around 5 gigahertz, and the typical anharmonicity parameter delta is around negative 340 megahertz. In this paper, for the physical qubit layout and the connection, and for modularity purpose, we assume that the physical qubits are placed on the nodes of a 2-dimensional lattice. For the qubit connection, we consider 2 different physical connections. The first one is called 2-qubit bus. It connects 2 physical qubits on 2 adjacent nodes. The second one is called 4-qubit bus. For 4 physical qubits on the nodes of the square, it connects not only the qubit pairs on the edges, but also the pairs on the diagonals. The difference between these 2 kinds of buses are shown on the right. Just like the fabrication of traditional CMOS technology, There is also fabrication variance for superconducting quantum processors. Suppose we hope to fabricate one qubit with desired frequency f0. Its actual frequency after fabrication will be f0 plus the noise, nf. And nf satisfy a Gaussian distribution with zero mean and a standard deviation of sigma. This sigma is around 130 megahertz to 150 megahertz under IBM's state-of-the-art fabrication technology. So there is a natural randomness in the frequencies of the physical qubits. However, when the frequencies of nearby connected qubits satisfy some conditions, a unique defect called frequency collision will happen and bring unexpected degeneracy. Here we list 7 different frequency collision conditions based on IBM's technology. For example, the first row shows the first condition. It means, suppose we have 2 qubits J and K connected by a bus. If their frequencies Fj and Fk are approximately equal with a threshold of 17 megahertz, the frequency collision happens between them, and we have a hardware defect here. Due to such inherent randomness in the fabrication process, we cannot fully mitigate the frequency collision problem, even if we can carefully select the pre-fabrication qubit frequencies. And naturally, if we have more qubits and more qubit connections on a superconducting quantum processor, the probability that we encounter frequency collision after fabrication will increase, and the yield will be low. So now we have an intrinsic trade-off here. For a superconducting processor, if we have more qubits and the qubit connections, we'll have better performance because the overhead in qubit mapping can be reduced. But the yield will also be lower because the probability of frequency collision is increased. The question we hope to answer in this work is that, okay, can we optimize both the performance and the yield for a superconducting quantum processor simultaneously? And we propose to solve this question by trading in the programmability of a superconducting quantum processor. We propose to have application-specific architecture designs, and these designs will have both high performance and high yield for some specific applications. Yeah, briefly summarize our contribution. We propose an end-to-end design flow for efficient superconducting quantum processor architectures. For a given quantum program, we first profile it and extract some profiling information. This information is then fed into an architecture design flow. We also consider the physical constraints here, and finally, our design flow will generate efficient architectures for different applications. Yeah, in the rest of this talk, I will introduce the profiling methods and our 3-step design flow. First, let's talk about the profiling. There are many different kinds of information in a quantum program. What we should focus on? What feature in a program can connect the performance and yield? The answer is the 2 qubit gates. On one hand, the qubit mapping problem is caused by the execution of 2 qubit gates, and it is the performance bottleneck here. On the other hand, the underlying hardware that are employed to support 2 qubit gates, actually the qubit connections, cause the frequency collision problem, because the frequency collision only happens on connected qubits. So that in our profiling, we just get rid of all initialization, measurement, and single qubit gates, and only keep the 2 qubit gates. We build a graph based on the 2 qubit gate information. Each node represents a qubit, and 2 nodes are connected if they have 2 qubit gates between them. The weight of an edge is the number of 2 qubit gates between the 2 connected nodes. And based on this graph, we can have a weighted adjacency matrix for each quantum program. Yeah, this is a simple profiling. But before getting to the hardware design flow, let me first introduce like some profiling results of realistic quantum programs. Here we have the result for 2 different programs. And we can easily find that there is a strong pattern here. For the program on the left, the numbers of 2 qubit gates between qubit 0, 1, 1, 2, 2 and 3, and finally to 6 and 7 are fairly large. However, the number of 2 qubit gates outside this, like this 0 to 7 chain, is very small. This observation suggests that, okay, the number of 2 qubit gates on different logical qubit pairs can vary dramatically on a real quantum program. And a straightforward hardware design for this program, for example, is to have a physical qubit connected in such a chain. And so that most 2 qubit gates are directly supported. And we can use mapping to implement the rest. But this design could not support other programs well. For example, for the program on the right, it has a different pattern marked by this red circle. There are a lot of 2 qubit gates between qubit 7, 8, 9, and qubit 10, 11, 12. So we have the second observation here that different quantum programs have different 2 qubit gate patterns. Therefore, we hope that our hardware design flow can automatically generate different architectures for different program patterns. Now let's get into the architecture design flow. It has 3 steps. The first step is about qubit layout. That is where we should place the physical qubits on a substrate. In this research, we are still using a 2-dimensional substrate. And we further assume that the physical qubits are placed on the nodes of a 2-dimensional lattice to make these qubit placements manageable. The objectives in this step are for 2 qubits that are strongly connected. We put them on adjacent nodes so that the large number of 2 gates on them can be directly supported. And for those 2 qubit gates on 2 nodes that are not connected, the number of additional operations for remapping should be minimized. Therefore, we design a heuristic algorithm based on these 2 objectives. And here we have a simple example. We start from an empty 2-dimensional lattice and then place the qubits based on the profiling result. The basic idea here is to place the important qubits first. In this picture, we first place the qubit Q4 because it has the most 2 qubit gates. We place it in the center. And then we place Q0 because it has the second most 2 qubit gates. Q0 is placed right near Q4 since they are connected. This is the illustration of the basic idea, and you can check the details of the qubit placement algorithm in our paper. Now, after this step, all the qubits are now placed on a 2-dimensional substrate. The second step is about how to physically connect those placed qubits. Actually, the physical qubits can be connected in a very flexible way, and in this paper, we only consider the design decision between using 2 qubit buses or 4 qubit buses. These 2 buses, as I just introduced in the background, are commonly used in IBM's existing chips. In this step, we start from a baseline that, okay, 2 qubit buses have been applied on everywhere possible, and we hope to replace some of them with 4 qubit buses. The difference between these 2 different types of buses is that, okay, consider 4 qubits in a square. 4 qubit buses could provide additional connections on the diagonals, and that's the only difference. But as I just talked about the trade-off here, more connections will improve performance but lower the yield. So we hope to only employ 4 qubit buses on the positions that could benefit the performance most. The first thing we need to do in this step is to estimate the benefit of applying a 4 qubit bus for each square in this lattice. Since the only difference is the connection on the diagonals, we use the sum of the numbers of 2 qubit gates on the diagonals to represent the potential benefit of 4-cubed buses here. For example, in the green square here, we use the number of 2-cubed gates on Q0, Q3, plus the number of 2-cubed gates on Q1, Q2 to indicate the benefits. But there is one physical constraint we must consider. 4-cubed buses cannot be applied on 2 nearby squares, otherwise there will be 2 physical qubits connected by 2 different buses, and we don't want to see this on a realistic design. And as a result, applying 4-cubed bus in one square will immediately block applying them on its 4 nearby neighbors. So we designed a filter here to reflect the effect of this constraint. For example, for the real benefit, the filtered benefit of the green square, we use the original benefit from it minus the benefits from its 4 nearby neighbors, the blue squares. And such a filter will show the effect of this constraint. Finally, we can select those squares that are expected to benefit most from the 4-cubed buses, and then apply 4-cubed buses on them. After these 2 steps, we already have the design of qubit layout and connection. The last step is to determine the frequency of each qubit, which I call frequency allocation here, to minimize the frequency collision probability after fabrication. This is actually a hard optimization problem with a large search space. So we design a step-by-step heuristic local optimization algorithm here. We start from the center of the target design. For the example here, we start from Q5. And then we traverse all qubits from the center to the peripheral. For example, we first determine the frequencies for Q1, Q4, Q6, Q9, and Q10. They are directly connected to the center Q5. Then we go one step ahead and add more qubits like this. And finally, we will iterate over all qubits. Each time we add a new qubit, we will try all possible frequencies, evaluate by simulating a yield rate, and select the one with the minimal frequency collision probability. And that's all for the architecture design flow. Now let's introduce our evaluation. For each architecture generated from our design flow, we hope to know its design complexity and the performance. We evaluate the hardware complexity by simulating the yield of the architecture with a yield simulator. We built it by ourselves. The yield model is from IBM. For the performance, we use the post-compilation gate count, and more gates here indicates a lower performance. The baseline architectures used for comparison here are 4 general purpose architectures from IBM. The qubits layouts have 2 options, 2x8 lattice, 4x5 lattice. And the connection also have 2 options, which are only using 2-qubit buses or use 4-qubit buses as much as possible. The frequency design is the IBM's 5 frequency scheme from 5 gigahertz to 5.27 gigahertz. Now let's take a look at the results. In our experiments, we have totally 12 architectures for 12 different programs, and you can check them in the paper. And here I will only discuss one typical result. This figure shows the yield versus performance for several different architectures for one specific program. The x-axis is the inversed and normalized gate count. Since it is inversed, then we know that data points on the right indicate a better performance. The y-axis is the yield. Data point on the top will have a higher yield. And we have a lot of experiments there. And here I highlight the overall comparison against IBM's designs. The 4 red diamond data points are for IBM's baseline architectures. And those blue triangles are generated from our design flow. labeled by an EFF. And there are several architectures with a trade-off between performance and yield in this data series, because we can select different number of Fokker devices here. We can see that with a almost a similar performance, our architectures are much simpler with a significantly higher yield rates. We also have other experimental configurations to provide a breakdown about how each step in our design flow affects the final results, and you can check them on the paper. A brief summary of the result is that our architectures provide similar performance with about 1,000 times higher yield. And among them, about 10 times yield improvements come from the third step, the frequency allocation itself, and about another 100 times yield improvements come from the architectural optimization from the first two steps. Finally, let me conclude this talk by discussing about the future work. Actually, this paper is only an initial effort in this direction, and it will only explore a small portion of a very large design space. The profiling measured in this paper aggregates all the 2-qubit information without considering temporal information. But we believe that finer grained profiling will bring more information for architecture design. One important limitation is that our design flow only supports one program each time per architecture. So there's a bad programmability. In the future, we hope to add some programmability and support a group of similar applications. And also, the design space exploration is still limited, and we hope to explore more flexible qubit placement and connection in the future. We also hope to figure out whether it is possible to perform global optimization for the frequency allocation. That's all for my talk. Thanks for your attention.